Good morning, good afternoon, or good evening whenever you watch this lecture. My name is Joris Melkert and I'm Senior Lecturer in the section of Flight Performance and Propulsion. And today we're going to talk about aircraft performance. Actually, we're going to talk about the best performance of an aircraft. And we do this because finding the best performance of an aircraft is very important in the framework of sustainability. We want to find the best performance, so that we minimize the environmental impact of the aircraft. So today's topic is best performance of an aircraft. And we know by now that the lift to drag ratio of an aircraft is a very important parameter in this sense. It's actually a measure for the aerodynamic efficiency of the aircraft. So what we want to do is we want to find the largest value of the lift to drag ratio. So mathematically speaking, we want to maximize the lift over drag ratio. And what we also want to figure out is, what does it mean for the pilot? How does a pilot have to fly such that he or she flies at maximum lift to drag ratio? Now let's try to do that. Here we need to start with the drag polar. The expression for the drag polar, you've seen this before. You can write that down as CD. The drag coefficient of an aircraft is the zero lift drag coefficient, CD0, plus CL squared, the lift coefficient squared, over pi AE, in which you recognize that the A, the aspect ratio of the aircraft, the wings of the aircraft. Mathematically equivalent, you can also write it as CD0 plus a constant K times CL squared. Now let's make a graph of this, because that's very handy to see. I like to make graphs, so I advise you also make graphs, because then you get more insight. And for this graph, we're going to take this aircraft, Boeing 777, the 777. In the literature, I found the value for the drag polar. CD0 equals 0.0135 plus 0.0432 CL squared. I want to make a graph of that. This is how the graph looks like. On the vertical axis, I have my drag coefficient, and on the horizontal axis, I have my lift coefficient. But this is not the way we normally make this graph in aviation. What we do something weird. We interchange the axis. We flip the axis. So normally the way we draw this graph looks like this. Where we now have the drag coefficient on the horizontal axis and the lift coefficient on the vertical axis. And I can fly at any point of this curve, so let's take this point, and then I can read the values for the lift coefficient and the drag coefficient, and then divide the two, and then I have my lift to drag ratio at this specific point in the curve. And that is 15.0. The question is this the optimum value? Is this the best value? No. That's 20.70. Now what does this mean for the pilot? What do we need to tell the pilot? Okay, pretty straightforward. Look at your L over D meter and make sure the needle says 20.7. Okay, let's see where the meter is. There is no lift over drag indicator in this cockpit. Okay, this is an old cockpit, still analog indicators. Let's look into a modern cockpit and let's try to find the lift over drag meter. No, it's neither. No lift over drag meter. Okay, what do we need to do then? Well, actually, there's another way of doing this. You don't need a lift over drag meter to do this. There's other ways, and they're more handy for a pilot to tell him or her how to fly at maximum lift to drag ratio. And for that, I'm going to do a trick. The trick is as follows. I'm going to take an expression for the drag force, capital D. And the trick is that I'm going to multiply it by 1. Mathematically, that's fully sound. I can totally do this, no problem. And then in the next step, I'm going to replace this 1 by L over L, the lift over the lift. Again, mathematically, totally sound. And then the next step is that I'm going to maneuver this lift force a little bit. I'm going to say it's D over L multiplied by L. And if you look very carefully, you see already the lift to drag ratio in this equation. You see the reciprocal value, D over L, but the lift over drag ratio is there. Now, we need to make one assumption here. We need to assume that the aircraft is flying a horizontal level flight, stationary flight, where all forces are in equilibrium. The lift force is equal to the weight force, and the drag force equal to the thrust. And then I can replace one of these lift forces in the equation by W. That I have done so, and I also now made the switch between lift and drag forces to lift and drag coefficient. So my drag equals CD over CL times the weight. Then one more step. We need to look into one moment in time. and at that one specific moment in time, we can say that the weight of the aircraft is constant. And then looking into this equation, when weight is constant and we want to maximize L over D, meaning minimize CD over CL, we can see that flying for maximum lift to drag ratio, it means you need to fly at the point where the drag is minimal. So we need to tell the pilot to fly at the point where the drag is minimal. Okay, let's make a graph again, but now a bit different graph, in which I have in the vertical axis, I have my drag force, and now on the horizontal axis, I have my airspeed. And that's important because a pilot has an airspeed indicator. So using the airspeed as a means to tell the pilot how to do things is handy. And you need to find a point for minimum drag. And that's the point where the red dot is. If you have found that red dot, you can read the value for the drag, and you can also find the value for the airspeed that belongs to that. So what we need to tell the pilot, when you need to fly maximum lift to drag ratio, you need to fly at an airspeed of 130 meters per second or 468 kilometers per hour or 253 knots. And that is the point where the pilot needs to fly. Is this the complete story? No, there's more. We also need to take into account the performance of the engine, because the engine is not a machine that performs the same at all airspeeds. And we need to take into account the fact that the weight of the aircraft is not constant, but it will go down when the flight continues because we burn fuel. But that's maybe for next year's lecture series.